Okay, everybody, let's take some time and go through these. Okay, so I expected you to be a little rusty. What I didn't expect was you to be, I don't know, a little extra rusty. Okay, so let's take a look. So real quick, so number 3, we get lucky because that is a perfect square, right? So the answer to that is just 12. Okay, good. Now, when you jump to, before I go to, oh, all right, number 6, fine. So 6, now 12 is not a perfect square, right? So I'm not just gonna grab my calculator and turn it into a decimal, I'm gonna simplify that radical. Okay, so if you remember how to do this, it's just as easy as thinking of, oops, there we go. I need to think of the numbers that divide into 12, and I'm looking for one that's going to be a perfect square. So although it's true that 2 times 6 gets me 12, 2 isn't a perfect square and 6 isn't a perfect square. So that's not going to help me any, right? I'm looking for perfect squares. Remember what the perfect squares are, right? I guess am I jumping the gun? The perfect squares are 1, 4, 9, 16, 25, and so on, right? Those are what we're looking for. And you want to find the largest perfect square that divides into a number. Otherwise, you're just going to have to keep doing it over and over and over again. So the largest perfect square that happens to divide into 12 is 4. So you literally split this up into the square root of 4 times the square root of 3. That's still 12. And then this negative is just kind of hanging out in front. I know what the square root of 4 is. It's just 2. So this thing just simplifies to be that. That's it. I'm done. How do I know that I'm done? Because I look at the thing under the radical and I can't go any further. I can't, there's not another factor of 3 that's a perfect square. So I'm finished. When I jump to 9, now I have a situation because I have, I'm trying to add and subtract some radicals, and I have this one here. There's nothing, I can't simplify this one. 2 root 5 doesn't simplify again, root 2 doesn't simplify again, but this one sure does. So same thing I did on number 6. I want to think about 45, numbers that divide into 45. And I'm specifically looking for the largest perfect square that goes into 45, which happens to be 9. So this is going to split into 9 and 5, and that negative just comes down for the right. That's all. So that chunk right there just becomes negative 3 root 5. Bring down the others, plus 2 root 5 minus root 2. Okay, now that I have simplified all my radicals as much as I can I do any of these operations that they're asking me to do? Can you simplify this any further? Riley, go ahead. Yes, these are like radicals, just like terms, right? I can add 2x and 3x, but I can't add 2x and 3y, right? Because they're not like terms. Same thing applies with radicals. If they have the exact same radical, I can combine their coefficients. So negative 3 of these things, and then 2 of these things would leave me with negative 1 of these things. And then I still have this minus root 2. I can't go any further than that. They're completely different. It's like having x plus y. You can't go any further. You're done. That's it. So check your answer and make sure that that's as far as you went. And you didn't then try and like combine that root 5 and root 2 to make some abomination of like a root 7 or something. Make sure you did not do that. You didn't do it, did you? Oh, good. So that's it. That's my answer. 12. Oh, 12, you get lucky because everybody is already, they're all simplified and they're all like radicals. So when you combine them all, what do you get? Negative 4, you say? I agree. Negative 4 root 6. Agreed? Not so bad. All right. Flip. 15. Some of you went about this a way harder way by multiplying it together and then just factoring it back out. Silly goose. It's already factored. When you are solving this, right, and you already have it factored, all you have to do is set each factor to 0 and solve, right? So you'd have 1, 5r plus 3 equals 0, and 1 r minus 3 equals 0. Solve each one. One of them is a -3/5 and the other is a +3. Do you remember writing answers with these funny curly brackets? Yes. That's anytime you have I mean, you can always do it, but usually you see it quite often when you have more than one answer. And it's just, hey, I'm just listing off my answers. Order does not matter. If I said, hey, what are the names of your pets? It doesn't matter what order you give them in, right? It's the same idea here. It's just, you're just rattling off all the possible answers. It's not an ordered pair, right? That's a big difference. So there they are. 18, we've got a quadratic here you need to solve. This one's not factored. So hopefully you remember, oh, if it's a quadratic, I want to set it equal to 0. So I'm going to minus that 5b over. Remember this? And now when a is 1, we're so lucky because all I need are factors of 6 that add up to be a -5. What would those be in this case? A -2 and a -3. Remember this? It's been a while. I know. Double check that you didn't have a -6 and a +1 because those multiply to be a -6. You wanted a +6, so it's got to be these two, which means my two answers are +2 and +3. Okay, this is becoming more familiar. All right, 21. Ooh, another quadratic. So let's bring that over. 49n squared plus a 189n plus a 126. Let's cross our fingers and hope that everybody is divisible by 49. Is it? Oh, only by 7? Darn. Okay, but that's all right. If I am solving, I can divide both sides by a common factor. In this case, it sounds like 7. So 7n squared, 189 over 7 is 27. Okay, it's a little bit better. Now it's up to you to solve this however you're going to solve it. I hope you factored it. I hope you remember how to factor when a is not 1. There's a couple of different methods. I don't have a preference. I don't care what method you use as long as you have a method that works for you. So it sounded from what I heard, most of you do guess and check, which is where you find the factors of 7 and the factors of 18, and you find you literally just guess and check until you have like a pair that works. Yeah, does that sound like what you do? Is everybody affected by grouping, where you multiply a and c, rewrite and cut in half? You can do that too. Anybody do this fancy one called slide and divide? Have you heard that? No. Do you want to see it? It's so cool. I'll show it to you. You don't have to. You can do it however you want to do it. Let me show you slide and divide, because if you've never seen, I was floored. Okay. For what? Let me show you slide and divide. You start by multiplying a and c together. So 7 times 18 is 126. Now watch this. This is so crazy. I'm gonna drop it off for a minute. So this is the slide part. N squared plus 27n plus 126. One of the downsides to this method, though, is that sometimes your numbers can get kind of big. So now I'm going to ignore this 7 for just a minute. Okay, don't worry. I will bring it back into play. I'm going to factor this now like it's a normal trinomial where a is 1. Factors of 126 have to be 27. I don't know what they are. Six and 21. Watch this though. Are you ready? This is crazy. Whatever this was the slide part. I multiplied that 7 across. Now you have to do the divide part. You ready for this? You sneak in here, whatever you multiplied by. So in this case, it was a 7. You sneak in right here and you divide both of these by 7. If you can reduce the fraction, you do. And if it doesn't reduce, like this first one doesn't reduce, that 7 just sneaks around in front. I'm out of room, but I'll write it over here. So it becomes 7n plus 6. And then this one, 21 over 7, is just 3. What? Have you ever seen that before? It's crazy, right? But it works. Is that what you got? When you factored it, however you did it? Oh my gosh. So I love slide and divide. However, common mistakes are abundant because a lot of times kids do the slide, but then they forget the divide part. Or they do the divide part and they forget like what they're supposed to do with it. So, you know, if you're going to use it, you got to be careful. But yes, oh gosh, slide and divide, so cool. Anyway, however you factored this, you should get here. And then I just set each one equal to 0. So hopefully you've got your two values to be a -6/7 and a -3. Perfect. Okay, so again, whatever method you use, stick with it because you're probably pretty good at it. Or you were at one time, I hope. So maybe you just got to practice a little bit again and you will get right back there. Okay, last one, 24. Let's see. Another quadratic. Let's get all of our things together on one side. So it'd be a 24x squared minus 32x plus 8. And this time I can at least divide everybody by 8. And now you're just factoring this one. So here, I mean, you could do slide and divide, on all of them, but when your ends are prime, you might as well just do a guess and check, right? Because you'd have a 3x and an x. And then let's see, I'd want a
That'd be a 1. The +2 would be
oh yes, because I divided by 8. Oh, thank you. Oh my gosh. Thank you, thank you, thank you. So then I'd have a -1 and a -1. Is that right? 3x squared -1 plus 1. Yep. Whew. And so did you get your answers to be +1/3 and a +1? All right, cool. So I have already posted the answers to this on Jupyter. So if you are like, oh, I am terrible with blah, 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 I encourage you to practice a couple more just to make sure you know what's going on, because although this is not the focus of chapter 8, you need these algebra skills in order to be successful at chapter 8. Okay, particularly the radical stuff. And so I'm going to give you the note sheet, and I want to try at least, I want to talk about the, well, let me give this to you first. One, 2, 3, and 4. Why did we not have a 2-hour delay today? Were your notes there? That was terrible. Something for everything here. Ah. Missed opportunity. And 3. Okay, so if you take a look at that, can you try the fraction one right there? Let's just see if you remember how to handle square roots of fractions, simplifying those. Okay, we got an answer? Maybe? So first thing you should do, if you have a fraction and the whole thing is underneath the square root, try and reduce that fraction, right? If it's a fraction that can be reduced, awesome. Unfortunately, I don't think we can here, right? I don't have any common factors, do I? No. So, all right, too bad, so sad. But if there are, my gosh, do it because it'll save you so much work. So, do you remember that when you are taking the square root of a fraction, you can break it up into two square roots of just the numerator and just the denominator. So you can kind of handle them separately. So that's basically what I'm going to do. I'm going to handle the square root of 45, simplify that like I normally would. Handle the square root of 32, simplify that like I normally would. So 45 split up into 9 and 5. So that one's just 3 root 5, right? And then 32, although it's true that 4 divides to 32, there's a bigger perfect square, 16. So you want to try and find the biggest one, because if you don't, then you're going to be stuck with a radical that needs to be simplified again. You're making more work for yourself. It's like taking the fraction 50 over 100 and reducing it to be, I don't know, 25 over 50. Now you got to do it again. You're not done yet. You didn't reduce by the biggest thing you could. Any hoosers, so 32 would split into square root of 16, square root of 2, so that's just 4 root 2. So now you're here. If these numbers had a common factor, you could reduce them with each other. So as long as you have two numbers that are not under a radical, they can be reduced with each other. 3 and 4 don't, so I'm done there. If these two numbers had a common factor, as long as they're both under the radical, I could reduce them with each other. 5 and 2 don't. However, do you remember that you are not allowed to leave radicals in the denominator? Great question is why not? I wish I had an answer for you. Mathematically, it does not matter. It literally doesn't matter if there's a square root in the denominator. It's the same number. However, for whatever reason, someone at some point decided that you're not allowed to leave radicals in the denominator, and so we don't leave them. I'm not kidding. I wish I had a better answer for you. It wasn't until I was in graduate school, and so one of the classes was for teachers, right? So we're all teachers, but my professor was a professor of like normal students, right? And so we are all giving our answer to whatever problem it was. And he's like, why are you all doing this? We're like, you rationalize the denominator. And he's like, no, you don't. What are you talking? Like, he didn't even know what we were talking about. So we're like, yeah, we always have to rationalize the denominator. He's like, there's no reason to. There's literally no reason. Unfortunately, there is a reason for you. If you went to take like SATs or something, I would imagine that all their answers would have rationalized denominators. So if you don't know how to do it, right? So it's worth knowing, even though it's mathematically pointless, in my opinion. But anyway, so here it is. I can't leave that root 2 down there. Does anybody remember how to get rid of it? Go ahead, Sam.
So you multiply it by the top. Like you multiply the top and the bottom
By what?
by root.
Yes, you multiply by whatever that square root is on top and on bottom, which is really just multiplying by 1. So you're not doing anything, you're not like changing its value or anything. But look what happens. On the top, you get 3 root 10. As long as things are both under the radical, you can multiply them together. So downstairs, root 2 times root 2 is just 2, right? And then 2 times 4 gets me an 8. So that is going to be your fully simplified answer. I hope no one then tried to reduce that 10 with that 8. That's a big no-no. You can't do that. You can't reduce something that's in a root with something that's not in a root. Oh no, don't do that. But there you have it. So they either have to both be in or both be out. If you end up with a square root in the denominator, unfortunately, you are going to have to rationalize that denominator. Okay, even though my personal opinion is that you shouldn't have to, but it's not up to me. All right, so we feel okay? All right, so let's take a look at 8-1 now. Have Have you ever heard of the geometric mean before? Have you heard of a geometric mean? So let's cross out the word recall because you probably have no idea what that refers to. I know you know when I say, hey, find the mean of this set of numbers, I know you know what that means, right? Or no? Mean median mode, remember that from forever ago? You have heard of mean median and mode, okay. Another word for mean is just average. So test average is the same thing as saying, hey, what's your mean test score? Right? So you would just take all your test grades, add them together and divide by how many tests there are, right? Right? Yes? Okay. That mean is actually an arithmetic mean. You are adding things and dividing by how many there are. So when you learn that mean, it's really called an arithmetic mean. There's another type of mean called a geometric mean. And this, instead of adding the numbers and dividing by how many there are, you ready for what you do here? This is crazy. You're going to multiply them together and take, so let's say I have two numbers. If I multiply two numbers together, I would then take its square root, the square root of the product of those two numbers. If I had three numbers and I wanted their geometric mean, I'd multiply all three together and take their cube root. If I had four numbers, multiply all four, take the fourth root. Now, why would you ever do this? Well, let me give you a great example. Let's say you're in biology, you're growing bacteria for something or whatever. Let's say the bacteria grows by 20% the first hour. Let's say they grow by 30% the second hour. Let's say they grow by, I don't know, 32% the third hour. If you wanted to know, okay, well, what's their average rate of growth? It wouldn't make sense to do the arithmetic mean because percents is all based off of multiplication, right? So if you add it together and just divide by 3, it's not really giving you a true picture. So a better use would be using a geometric mean to multiply them together and take a cube root if it was 3 hours, for example. Okay, so that's kind of what geometric mean is. So let's fill in these dots right here. The geometric mean of two numbers A and B is the square root of their product. It's square root of their product. So we can kind of visualize this in two different ways. So the geometric mean, I'm going to call that x, would be equal to the square root of a times b. Or you can actually and this kind of fits in a little bit better with what we're going to be talking about with these triangles. It also works this way. A over x equals x over b. If you think about it, if you were to solve that for x, right? If you go ahead and cross multiply, you'd get a times b equals x squared, and then I'd take the square root of both sides. So I would basically end up right here. So these two are equivalent. Okay, so if you want to find the geometric mean between two numbers, you can use either because it really is the same thing. Oh, and you know what? We should specify that our numbers are going to be positive here. I mean, it only makes sense because we'll be doing it in triangles, so the sides of triangles are always positive, but let's stick in the mean of two positive numbers. All right, now how does this have anything to do with triangles? Okay, let me show you. So we have a theorem to write in here. Let's see, where will I stick this? I'm gonna put it right here. All right, when an altitude, do you remember what an altitude is? In a triangle? Altitude goes from where to where? Carson?
From the top of the vertex top, straight down to the bottom of the base.
Yes, it has to drop perpendicular. So from a vertex, you're going to drop perpendicular to a base. Okay, so when an altitude is drawn in a right triangle, from the right angle, the hypotenuse is split into two parts. I'm going to pause here and let you catch up, because I want to make sure that everybody understands what I'm talking about when I get to this next part. I will say this section is a little confusing at first, but I promise once you get the hang of it, it's really not that bad. But you got to pay attention, because if you're not, then you're going to be completely lost and you'll have no idea what I'm talking about. You might already have no idea what I'm talking about. It's all right. I feel like it always makes more sense when you actually put numbers, like numbers on the triangles in that triangle. I don't know. That's what works for me anyway. But it's important that we get the words out. I'm gonna shut the lights off too. I don't know if that helps. Let me turn this one on. A little better. Okay, so before I finish the theorem, let's just look at the picture and sort of wrap our minds around this. So in the picture, we have a right triangle. My original triangle is a right triangle, ACB, right? And so it says when an altitude is drawn in a right triangle from the right angle. So that's exactly what I have. I'm dropping an altitude from the right angle. So what has that altitude done? It split my hypotenuse into two pieces. I have a piece right here, AD, and I have another piece over here, DB. Okay, so far are you with me? Right triangle, from the right angle, I drop an altitude. It has broken the hypotenuse into two parts. So here's the weird part. The altitude is the geometric mean of those two parts. So this is telling us that the length of the altitude, so CD in this case. So CD would be equal to the square root of those two pieces of the hypotenuse multiplied together. AD times DB. Or if you prefer to use the proportion setup instead, you certainly can do that. It's the same idea. So here's how I set up geometric mean with the proportion. I always put whatever is the geometric mean in one set of diagonals. So CD is my altitude, so that automatically goes in one set of diagonals. And then whatever it's the geometric mean of the two pieces goes in the other slots. So AD and DB. You also don't have to worry that much about like, okay, well, how do you know which piece goes, like, how do you know that was AD and not DB? It really doesn't matter because you're going to multiply diagonally, right? So it doesn't matter if you do 2 times 3 or 2 times 2, who cares? You just need the geometric mean to be in one set of diagonals and then the pieces in the other. So these are going to get you the same answer. So it doesn't really matter which one you go with. I don't know why. I always lean towards the proportion one, even though I feel like this also kind of saves you a step, but I don't know. You do you. So let's try this with some numbers, shall we? Okay, let's say I did. Start off with a right triangle. Oh, let's get this in the screen. I have a right triangle. I then draw an altitude from that right angle. If I wanted you to find the length of X, knowing that this was 4, and let's say this one was 6, you can find it. Give it a try. The altitude is the geometric mean between the two pieces of the hypotenuse. When you get your answer, we don't want decimals. Really, this whole chapter, we're going to stay away from decimals. We are going to, if it's a radical, we're going to simplify those radicals. Okay, we are really not touching decimals here. Did you get an answer? What answer did you get? Sam, tell me.
I got 2 6.
2 root 6. Do you guys agree? So do I. So just in case you didn't get it. So it really doesn't matter which of these two you're gonna, I'll do both, just so you have both sort of done out. If you like this equation, that's basically what you're doing. So the altitude is the geometric mean, which means if I multiply these two together and take its square root, we get the square root of 24, which if you simplify that, splits into 4 and 6. So yes, 2 root 6. If you prefer the proportion, set up your proportion, whatever is the thing that's the geometric mean. In this case, it's X. That goes in one set of diagonals, and then the pieces go in the other, 4 and 6. When you cross multiply, you'll see pretty quickly that I'm basically getting here. X squared equals 24, and then I square root both sides. So I still get that 2 root 6. Either way, whatever makes more sense to you, okay? Now, there is a corollary of this. Actually, you know what? Maybe let me do one more example before I move on to the corollary. I don't have enough room on here, so I'm going to use another sheet. I'm sorry. I'm going to draw the triangle a little bit differently. Try and throw you off the track. What if that were X, this were 8, and this were, I don't know, 3? Can you solve for X here? Nothing is drawn to scale, obviously. Okay, we got an answer this time. Who's got this one? Oh, we're less confident. It's the same idea. Did you put all the pieces in the right spot? Let's see. Remember, it's the altitude that's the geometric mean. So the altitude has to go in each spot. And then the pieces go in the other spot. So in this case, it's a 3 and an X. You with me? So now I'm going to cross multiply. I get 64 equals 3x divided by 3 divided by 3. Whatever 64 divided by 3 is. 21 and a third. Is that right? Am I right? I am?
Yeah.
Yeah, definitely not drop scale. But does that make sense? Okay, cool. If you had used the other equation, you would have had what? 8 equals the square root of 3x. So what do? Isabella? Yeah, square both sides, right? Square u, I get 64 equals 3x, and you end up with the same thing, right? 21 and a third. So are we reasonably comfortable with this? Because the next one is real weird. This one I feel like isn't so bad. The next one is, I mean, it just takes a while to get used to, that's all. But I don't want to move on away from this if you're like, I literally have no idea what you're talking about. But are we comfortable? Okay, okay. All right, so there is a corollary to this theorem. I'm going to stick it in right here, and then I'll do some examples on another sheet because I definitely won't have enough room. All right. So how will I? Yeah. Okay, corollary. All right, ready for this? Each leg of the
8.2.
no, this is still 8-1. Each leg of the original right triangle is a geometric mean between the piece of the hypotenuse it's connected to and the entire hypotenuse. All right, let me give you a moment to jot that down, and then I'll show you exactly what I'm talking about. I'm going to zoom in a bit. Or out, because I don't know which way I'm going. Man, the lighting is really terrible today. I'm sorry. Let's see if I put up my fancy folder, if that will help. Oh, that does help. Okay, good. Okay. You got that written down? No, let me explain what in the world they're saying. So I'm gonna redraw our same original triangle that we had. So it was A, C up top, B over here, right angle right there, altitude drawn, and that was a point D. Oh, thank you. There we go. Okay, so I just redrew the same original triangle that we had printed over there. So here's what this one's saying. Nothing to do with the altitude on the inside. Okay, I mean, sort of. I'm looking at a leg of the original. So remember, the legs are the two sides that form the right angle. So I have a leg here, CA, and I have another leg over here, CB. Okay, we're going to talk about just one of them at a time. So if I'm talking about leg CA, this corollary is saying that CA will be the geometric mean between the piece of the hypotenuse it's connected to. So I still have my hypotenuse broken into two parts. One of those parts is connected to CA, right? AD is the one that's like the piece of the hypotenuse that's touching CA. So that's the part of the hypotenuse it's connected to is AD. And then the entire hypotenuse is obviously AB. So that's what this corollary is saying. Okay, if you like the proportion better, fine. So CA would go in one set of diagonals, and then the piece of the hypotenuse it's touching, AD, goes in one, and then the whole hypotenuse in the other, AB. The same thing applies for the other leg. So you try and fill this out. What would CB be equal to? The square root of what times what? BD times what? Yes. The piece of the hypotenuse it's attached to, in this case is DB, times the whole hypotenuse AB. Hooray! If you like it better as a proportion, okay, cool. CB in each set of diagonals, DB, and then the whole thing AB. Oh, sorry. There we go. Let us try some problems. Okay. Does everybody have what they need right there? Wait, I'll put some numbers in while we finish up. Let's try, if that's X, let's make this a 2, and maybe that can be a 10. All right, let's try this. I give you that. You can solve for X. X is just one of the legs of my original big triangle. So that's got to be the geometric mean between blank and blank. So see if you can put in those pieces. So I'm going to help you set this one up again if you haven't already. So I have one of the legs of the original. The legs are the geometric mean between, so X is going to go in one set of spots, between the piece of the hypotenuse it's connected to. So what's that in this case? 2, right? 2 is the piece there, is the value of the piece that it's connected to. And the whole hypotenuse, which would be 12. Yes. So X is going to be the square root of 24, right? So just simplify that because you'll get X squared equals 24, square root, square root. So that's just 2 root 6. Same triangle, same numbers, find me y. Please make sure you're trying these. I don't want you to be super lost on this whole section. So the only way to know that you know what I'm talking about is if you do them. Pencil to paper. How'd you do? So y is another leg of my original triangle, right? So y is going to be the geometric mean between the piece of the hypotenuse it's attached to. So that is 10. And the whole hypotenuse, which is 12. So this one's going to be the square root of 120. Oh, did you guys simplify that? What's that? Is it, what is it? Yeah, it doesn't go any further than that, right? 2 root 30. That's good to me. Same triangle, same numbers. Find me z. Oh. Not that I don't like the other chapters of this book, but 8's probably my favorite. Just saying. Oh my gosh. Wait till we get to, I think it was at 8-4. That's probably my favorite. You know what though? I really like circles too. I don't know. It's a tough call. Any hoosers, you guys got an answer for Z? Wouldn't Z be the geometric mean between what and what? Ten and 2, right? That's so when you have the altitude itself, it's the geometric mean between the two pieces of the hypotenuse, 10 and 2. So it does get a little, you know, the only way to make sure that you sort of solidify this in your brain is just keep practicing them. So we get z squared equals 20, square root, square root. So I end up with 2 root 5. So, all right, let me give you one more. And then I will give you your assignment for the day. So again, a right triangle with the altitude drawn from the right angle. And this time I'll tell you, let's make this 4. Let's make this X. Let's make this, I don't know, 10. And then could you then find yeah, let's go with it. So I don't think that there's a way to do this without solving for X first. Because then you're going to have more than one variable. So yeah, That's my advice. I would figure out what the value of X is first, which you can do. And then you should be able to find Z and Y. Ooh, that's kind of a good one. Nothing strong to scale, of course. Did everybody get 8/5 for X? Yeah, okay. Because if we had different values for X, then our values for Z and Y are definitely going to be wrong or different or something. I'm going to start going through, I'll find Y first, whatever. Y, someone tell me, would be the geometric mean between what and what? Go ahead, Patrick.
10 and 10.
So you're not, well, it'd be 10 plus X,
Oh,
right? Because you'd want the whole hypotenuse. But now that I know what X is, it's 8/5. Let's find the length of my whole hypotenuse. So 10 plus 8/5 is, oh, what is that? 58 fifths? 58 fifths. Okay. 58 fifths. All right, cool. So now I can cross multiply. I get Y squared. 10 times 58 fifths. I can at least reduce that. That's 116. Am I right? Did you guys get what I got? You gotta double check. And now square root both sides. So what goes into 116? 4 does. Anything bigger though? No, 4 goes in 29 times. So it's going to be 2 root 29. Are we the Grayman or not really? Yeah, we are. Okay. Just making sure. Okay, now I can go ahead and find Z. So Z would be the geometric mean between what and what? 8/5 and 58/5, right? The whole hypotenuse, the piece of the hypotenuse it's attached to, and the whole thing. So this one looks like it's going to be more annoying. 8 times 58 is what? 464. And 5 times 5 is 25. Oh, maybe it's not so bad. Right? Take the square root of both sides. We get lucky with the denominator. So that's just going to be 5 on the bottom. What goes into 464? Obviously 4 does. 16 goes in. So 464 divided by 16 is 29. So I get the 4 root 29. How about that? Did you get it? No? Do you know where you went wrong? What?
I didn't get C.
Oh. Did you have the proportion right? Oh.
That's why.
So how do we feel? It's a little weird, but with practice, not so bad. So most important things to remember, if you have the altitude on the inside, that's the geometric mean between the two pieces of the hypotenuse. You just do piece and piece. If you have one of the legs, it's the geometric mean between the piece it's attached to and the whole hypotenuse. Weird, but totally doable, especially with more practice. Allow me to give you that practice. Here is your homework for this evening. We're only going to do 9 problems. There they are. Page 289, 31 to 39. Okay, we got a good 15 minutes right now. You could probably get a nice chunk of that out of the way. I'm going to go open this up on Jupyter for you.